You can start now.
Am I audible, sir?
Yeah, audible, ma'am. Audible.
So good evening, a very good evening to everyone. So the Directorate of Admissions and the Academic Outreach in association with the Amrita School of Physical Science, Coimbatore is conducting a weekly educative webinars on every Saturday that would be helpful for the aspirants to be updated about the various trends and would guide to choose the right stream of their choice. So in this episode, today we are having Dr. A. Ramesh Babu, Assistant Professor, Senior Grade, Department of Mathematics, Amrita School of Physical Sciences, Amrita Vishwavidyapeetham, Coimbatore, will be delivering an informative session on mathematical methods in semiconductor devices. So all the students, please note, if you have any query, you can please note it down, and at the end of the session, you can put it in the chat box and sir will help you out to clear your all the queries. So over to you, sir. Thank you.
Thank you, madam. So I welcome you all for this Saturday series lecture, and I really thankful to the Director of Admission for hosting this Saturday series lectures, which is an inspiring one, which is inspiring the students how the role of mathematics or mathematical methods in engineering, application of engineering, in general physical sciences. So we will look into that, the methods which we have so far studied in schools. What are the methods we have done? What are the methods known to us? And these methods are how effectively applied in engineering, basic engineering, or kind of semiconductor devices, which we are going to see today. Before that, I will give some tips or some idea about mathematics of we call it mathematical physics. We call it so physics with mathematics. What I am going to do is today is you should know the basics physics and as well as basic mathematics. Then what is the role of this mathematical physics in engineering? That's what I am going to do. I'm sharing my yeah, okay, cool. Well, so the mathematical methods in semiconductor device is a topic of this Saturday series, and I'll give a short introduction on that. My plan of talk is like this, and I'll give some introduction to this mathematical methods to semiconductor device, and what is the role of this semiconductor devices in engineering, and how it can be modeled by this using this mathematical methods, and derivation of this model equations, and after that the necessity of numerical approximation to model equations, and there are few methods I'm going to elaborate or kind of interest. One is a very important method which we are often using in numerical approximations or numerical simulations to this model equations. That is a finite element method, And some MATLAB program is also we have done it, and that's all. This is my plan of talk. So this semiconductor device model. So what I am doing here is some mathematical models to the semiconductor device and numerical solutions of that. So first we go by the mathematical modeling. So the numerical modeling of the electromagnetic or thermal behavior of semiconductor device is a challenging task. It's not easiest one to model it. And in general, the mathematical models are coupled non-stationary system of parabolic and elliptic partial differential equations, which is in a two-space dimension or three-space dimension, and which is also involving exponential nonlinearity. First of all, I have to explain that what is the meaning of coupled equation. More than one equations and the dependent variable and also independent variable. It's a coupled. A non-stationary means that it's also allowing the time variable of parabolic and elliptic partial differential equations. So maybe a parabolic type or elliptic type of PPD. And this kind of exponential nonlinearity means that the equations having a nonlinear nature, but exponential nonlinear nature. That means we cannot, the complex system, the complexity has been in the next level. And the flow of current in the semiconductor device, which is a convection dominator. I will tell you later what do you mean by convection dominator. The current flow is nothing but in a semiconductor device, the electron movement from is nothing but your that's an understanding of current flow. And the next one is this convection dominator means that the doping profiles are essentially discontinuous, and it has a jump from large positive values to large negative values, which is across this a thin layer, extreme thin layer. In this slide, I will give you Van Roosbrook equations, which is my targeted equation, Van Roosbrook equations. Usually it is a coupled equation. Sometimes it's a single equations. Okay, so once we incorporate more number of ingredients or material properties, then we are having a coupled equations. This Van Roosbrook equations and the initial and boundary conditions for typical semiconductor device models, which is an examples of singular perturbation problems. So what I am going to do is this Van Roosbrook equation is considered to be as a singular perturbation problem. Later on, the later part of this talk, I will give you the idea of singular perturbation problem as well. So the solution of such problem, that is singular perturbation problem, that is we call it SPP. These problems which exhibit boundary as well as interior layers. And there is a small regions of the device in which some physical quantity, we call it electric field or current density, which these quantities has a large gradient. In this slide, we will see some basic ideas of semiconductors. For example, if I am taken up an isolated atom or electrons can only occupy discrete energy levels in an isolated atom. But in that atoms are organized in lattices. Each of these discrete energy levels split into continuous band of energy levels because of the atomic interactions. So that the separate energy bands may merge into the single band when the spacing between the atoms decreases. If the spacing is again reduced, the single bands may split again into disjoint bands. This is happening in this semiconductor devices. These bands are separated by forbidden energy region in which there are no allowed energy levels. So examples of such disjoint bands are, we call it a valency band and a conduction band. The difference in the energy of these bands is termed as band gap, that is always denoted by capital EG. And this band gap is an important parameter in solid state physics, since it allows us to classify solids into three component groups. We call it insulators, semiconductors, and conductors. So to describe the behavior of the semiconductors, we have to introduce the concept of positively charged holes. When the negatively charged electrons is raised from the valency band towards the conduction band, then it leaves a positively charged hole in the valency band. Such holes can contribute to the conduction of the current. So conduction, which results from an interchange of holes and electrons in the nearly filled valency band, is always referred as hole conduction. If an electric field is applied, then both the electrons in the conduction band and the holes in the valency band gain that kinetic energy, and current conduction results. So in the models describing the behavior of the semiconductor devices, equations for both electrons and hole currents are used. Now we consider this intrinsic semiconductor. That is what a pure material. Intrinsic semiconductor contains a negligible number of impurities compared to the number of thermally generated electrons and holes. So for an intrinsic semiconductor in equilibrium, the electron concentration in the conduction band equals the hole concentration in the valency band. So you can easily understand the meaning of electron concentration and hole concentrations and all. That is the electron movement on a particular space. That is what we called electron concentration. This concentration is called intrinsic carrier concentration. It is always denoted by N interior. That is what intrinsic carrier concentration, N int. And the types of material, I'm going to give you an overall view of this slide, in this slide. Conductivity properties may also influence by introducing a small number of impurities atoms into the semiconductor lattice. So I already told you that lattice is nothing but a ordered electrons and holes. That is what we called lattice. This process is called doping. So doping is a process. Hello.
So there are very few participants. Can you wait for others to join?
Oh, okay. I think, okay, fine. I can reshare it. Hello.
Any issue, sir?
Yeah. Shall I
Yeah.
proceed or wait for some time?
Yeah, no, proceed. We will ask you the Q&A at the last.
Okay, someone is asking to stop. I think, shall I proceed now? Okay. So this is what doping process. Doping process is nothing but a process in which there are some small number of impurity atoms that will be that is included in the semiconductor lattices, so that the intrinsic property turned into extrinsic property. Like the resulting material is, we call it extrinsic. So two kinds of dopant atoms can be implanted, namely those producing one or more excess conduction electrons and those accepting electrons and producing the holes. So in the former case, that is the first case, that more excess conduction electrons and accepting that electrons, we call it, it's a dopant is called a donor, whereas the second case, we call it it's a acceptor. So we call it a donor and a acceptor. So the resulting semiconductor material is said to be of N-type or P-type respectively, whether it is a donor or a dopant or acceptor. So I'm very much interested on the extrinsic semiconductor material now. So by introducing impurity concentrations, several orders of magnitude larger than the intrinsic carrier concentration. So the extrinsic material can be turned into good conductor even at a room temperature. So semiconductor devices are formed by combining a number of different types of extrinsic semiconductor materials. The precise configuration is determined by the doping process, which is a current technology, consists of hundreds of steps. Each of these steps is one of the following. That is what epitaxy, crystal growth, ion implantation, diffusion, oxidation, lithography, etching, depot. There are many processes, right? And the order in which the steps are executed is crucial for end product. So each of the steps is very important, and the order is also very important. And because of the sequential nature of this process, there is a strong interrelation between the various steps. This implies that an adequate physical description of these process steps is needed so that the simulation has to have a practical value. It has a practical value. And really, it is fortunate as within a certain limitations, such a description is available for most of the steps. So the goal of the process modeling is to provide such a description. The most important basic element is a p-n junction, which is obtained when a piece of p-type material is brought into the contact with the n-type material. Okay, so the p-type material is nothing but holes corresponding to the holes, and n-type material corresponding to the electrons. So under thermal equilibrium conditions, a transitions region is then formed, which is devoid of mobile concentration, since the electrons and holes recombine on both sides of junctions. So this transfer of charge across the junction destroys the neutrality of p-type and n-type regions, since the fixed charges due to the ionized impurities are no longer balanced by the mobile charge carriers. So the transition region called a space charge region contains a double layer of charge, which creates an electric field that eventually inhibits any further diffusion of carriers. And because of this double layer, there is a jump in the electrostatic potential across this transition region. The resulting potential at equilibrium is referred, we call it built-in potential. For example, we could take up a silicon. This potential varies from minus 0.5 to plus 0.5 volts. And additional carriers can occur across the transition region only if external potential is supplied. And we come into that device model right now. So I'll give a schematic diagram as well in this slide. So a device consisting of two p-n junctions is a MOS, that is metal oxide semiconductor transistor. A thin insulating oxide layer, usually silicon dioxide, separates the gate contact from the silicon surface. Looks like this, and you can see here it's a source drain. So the electron movement from source to drain, and there is a one gate is here in the middle. So this is a substrate. So we are talking about a device model which exhibits quantum effects as well. So in the later stage, we will see that what kind of quantum mechanical effects is there at in between this source and drain. So the first equation I'm going to consider here is a Boseman transport equation. So this is a first equation. I deduce my Van Roosbrook equation from this Boseman transport equations. So this is a idea I'm getting out from fluid dynamics, this basic Boseman transport equation. So to understanding the behavior of the semiconductor device, we have to model this behavior of semiconductor devices, which is necessary to have a physical or mathematical model. So most models in use are derived from Boseman transport equation. This is a non-stationary equation, non-stationary first order equation, that is a dou f by dou t plus v dot grad x of f plus 1 by m times of f effective of x comma t dot gradient of this f is equal to q. I think this capital Q is a collision, collision operator, yes. And grad x and grad v denotes the gradient operators, that is representing by dou x1, dou x2, dou x3, and so on and on. And f effective is effective force, and f is a unknown, that is a probability density function for one particle. So this is a source equation, Boltzmann transport equation, which is usually you're considering any model of this devices, electronic or especially semiconductor devices, you're always consider this equation, Boltzmann transport equations. And the right hand side function, this capital Q, which is a very complicated structure, that is collision operator. So alternative forms are presented for the case of charged particles moving in the semiconductors. That is the capital Q is written as integral over R3, this P of x comma v dash comma t to x comma v comma t. This is one state and this is another state. X comma v dash comma t is one state and x comma v comma t is another state. So minus of P of x comma v comma t to x comma v dash comma t. So into dv dash. So this expression, this P of x comma v1 comma t to x comma v2 comma t, which denotes the probability that the particle is scattered from the state, one state to another state. And stated differently, it denotes on the other hand, we can talk about the probability that the particle velocity changes instantaneously from v1 to v2. That is the meaning of this above statement. So the Boltzmann transport equation was originally derived in the context of gas dynamics. And if we wish to use it to describe the movement of electrons and holes in semiconductors, several modification has to be done. Then only it models this semiconductor device. So in particular, the quantum behavior of the electrons and holes has to be taken into an account. That's very important. Now we talk about the coupled equations. So this leads to the modification. I told you that we have to do some modification in the Boltzmann transport equations so that which can model this semiconductor device nicely. So for this modification, what kind of modification I am going to do? It's very interesting. And this kind of modification, both the differential operators of this equation and collision operator as well. So the transport equation for each type of charge carriers must be used here. And the interaction between these different types of particle can be included by the additional coupling terms. So what are the coupling terms here I'm going to add with this single equation? It's very important for us. If these changes are made, the resulting system of equations describing the transport of electrons and holes in the semiconductor device which is kind of this equation. This is a coupled equations. One is dou fp by dou t plus 1 by h delta, same as that, which is similar to this Boltzmann transport equation. The only thing is I'm taken up, one is for holes, another one is for, the first equation is corresponding to the holes and second equation corresponding to the electrons. And the right hand side term, I have done some modification that apart from that collision parameter, I am adding one more RP of Fp comma Fn, that is an additional term. So that this coupled equation is modeling that semiconductor device. And this K denotes this wave vector, and Fp and Fn are the probability density functions of for holes and electrons respectively. Fp is for holes and Fn is for electrons. So these equations serve as a basis for most models used in semiconductor device simulations. A wide and now I'll move to this solution methods. That's what I'm going to do. The central part of this talk is about the mathematical methods in semiconductor device models, equations. So I'm looking for this solution methods for this kind of system of Boltzmann transport equations. So what I'm going to do with this? So a wide variety of mathematical methods has been developed to obtain a solution of approximate solution of this Boltzmann transport equations. Some of these methods attempt a direct solution, a common feature being their time-consuming character. So that there are some cases, especially the Monte Carlo techniques, that is integral techniques, something kind of integral optimization techniques. They are also applied to derive the solutions. For this reason, most device modeling programs to date still use the classical method of moments to obtain the approximate solutions. So I look into that. I'm concentrating with this method of moments. So this is it is always a fairly widespread due to its relatively simplicity and its utility for extracting the information or behavior from this Boltzmann transport equations. So it's a consequence of the fact that moments of the distribution function are related to the physical quantities, the first moment, second moment, and nth moment, and all. So the simplest way to approximate the solution is through the zeroth order moment. So the zeroth order moment is this one. M naught of x comma t is integral over f of x comma k comma t dk1 dk2. This is the wave factors, this k1, k2, k3. It's a vector quantity. So this, by using this zeroth order moment, we recognized this to be the concentration of charged particles under consideration. And previously we have seen the first moment, sorry, zeroth moment. Now we look into that first order moment. The first order moment looks like this: m1 of x comma t is integral over k times of f of x comma k comma t dk1 dk2. So it's an integral form. So which gives us essentially we are using it in a current density. And this current density is always evaluated from this first order moment by using this formula minus qh delta by m1 of x comma t. So in a similar way, physical interpretations which can be assigned to higher order moments. So I'll go for the second order moment, third order moment, and as well nth order moment. So the ith order moment is defined here as a tensor. It's a kind of tensor. mq1, q1, q2, and so on, qi of x comma t as integral over. Sorry, there is a. I think there's a mistake here. I think k1, k2, and so on, kn. So this Q1, Q2, and 7, Qj varies from 1, 2, 3, and 7 for all j's. So on multiplying the Boltzmann transport equation by this quantity kq1, kq2, and 7 kq all, and integrating over the momentum space. So the following equations are obtained for components of moments of different order. So that's what they are giving the formula. See, we are not much interested about all these things, and we just move to that some interesting numerical approximations to these equations. So in this way, we are having an infinite hierarchy is constructed in which the ith moment is directly related to the moment I minus 1th moment and I plus 1th moment. So the later higher order moment plays a role in the evaluation of mi is unfortunate. So means that closing relation has to be the specified in order to able to generate a finite number of equations of the form in this previous statements. So this can also be done in various ways, and the complexity of the resulting model depends on the number of moments taken into account. So I move towards drift diffusion model from this Boltzmann transport equations. So a reasonable steps is to formulate a model based on minimum number of moments. That's very important. Instead of taking up the ith moment, I plus 1th moment and all. So the resulting model which we are getting it here is a drift diffusion model that provides a useful description of the behavior of the semiconductor devices. So ultimately what we are doing is here is talking about the surface potential and current density and what will be the carrier concentration and all. So the electron concentration, sorry, not carrier concentration, electron concentration and all. So that's my preference. So the usefulness of the model is greatly enhanced by using sophisticated expressions for the recombinations and mobility and band gap narrowing parameters occurring in the equations. So the derivation of drift diffusion model, which requires the use of first two moments of the Boltzmann transport equation, so that the parabolic band structure is we are getting it, we are assuming it actually. So the resulting equations are the equation expressing the conservation of mass, often referred to the continuity equations for electrons. And this is the first equation, dou n by dou t is minus 1 by q times of grad x dot j is equal to Cn. And I will tell you what is the Cn, what is j, what is n, and what is q and all. And equation expressing the conservation of momentum, you are getting the another equation, dou p by dou t plus Vm grad x dot p plus p dot grad x of Vm plus and so on is equal to Cp. And the Cp is representing the time rate of change of P due to collision. So, Cn is nothing but time rate of change due to the collision for the holes. It is for electrons, that is for holes. So, by simplifying the above two equations, we finally getting this equation. We get minus q by mu times of n into Vm is equal to kT times of grad x of n minus nf. And equivalently, we can say that the current density can be written as kT in the right hand side, exactly kT grad x n minus mu nf. So you're getting a system of equations as a drift diffusion model that has which includes a nonlinear system of PDEs. So we have a Poisson equations of this kind, minus grad dot of epsilon times of grad psi is equal to q times of p minus n plus d. So the left-hand side term epsilon is very important for me, that epsilon is a small parameter and that psi is a surface potential. And the continuity equations for the holes and electrons are respectively the following: equation number 13 and 14, that q times of dou p by dou t is equal to minus grad dot jp minus qr, and this q times of dou n by dou t is equal to minus grad dot j minus qr. So Poisson equations, which we can, this is the 12 equation number 12 is a Poisson equation, that's the elliptic equation, which is solved in an entire simulation domain. Whereas the continuity equation, that is equation number 13 and 14, are restricted to the parts of the domain. For example, we consider that from source to drain, we have to model this entire region. We have to calculate the psi for the entire region for this Poisson equation. For the continuity equations, we are considering only one part, not the entire region. And here I am talking about the current density and electrostatic potential. So the current density is Jp and Jm, which are related to the electrostatic potential and the carrier concentration by this equation. I think Jp is current density for holes and Jn is current density for electrons. And we are getting this equation number 15 and 16. And the effective fields EP and En, which reflects the effect of this band gap narrowing. So which was given by this EP and En in a different way, that is E plus KT by Q times of grad of logarithm of N. That is what intrinsic concentrations. Remarks on the above system. So with the ongoing miniaturization of the devices, so if you're taken up the semiconductor device smaller and smaller, taken to the smaller and smaller, that phenomena which are neglected in the diffusion model are becoming increasingly important. The additional physical effects are taken account of in the hydrodynamical model, which is described by this, that is what convective term, which I told you, convection dominated models. So if the convection term is neglected, the resulting model is also referred as a energy balance model, which is not exactly meaning that real behavior of this semiconductor device. So the hydrodynamical model, which consists of the following system of nonlinear PDEs. First one is the Poisson equations, and another two are continuity equations for holes and electrons. And JPs or JP and JN are current densities. And this is current densities which are represented by through this EP and EN. And as you know that what is dP, dN and all. And the capital T is a temperature at any state, I think TP and TN. And this is EP and EN are represented through this psi. Psi is a surface potential, which is a solution of the Poisson equation. That is equation number 13. And N is an intrinsic concentration. That T naught is a temperature. And K is a wave parameter, and everything is fine. And here I told you that is temperatures of holes and electrons. And T naught is a lattice temperature. So almost we come to this concluding remarks of this device model. The first remark is about a drift diffusion model. So the drift diffusion model of semiconductor devices in either in 2 dimension or 3 dimension is defined as by the Van Roosbrook equations. So almost this is a Van Roosbrook equations, and these forms are complicated system of which forms a complicated system of nonlinear, non-stationary PDEs, which may be one is parabolic, another one is elliptic. So it's a very complex model. The second remark is the geometry of the devices in 2 or higher dimensions. Therefore, the domain in which the solution of the above equation is sought is which is usually complex. There is no general mathematical theory for such systems, and thus question of existence, uniqueness, or stability or smoothness of solutions which cannot be answered. The third remark is, so mathematical point of view, there is no general mathematical theory for such system. So we have to, again, I think it's a repeated one. So it's a third one. So there are cases where it is known that more than one solution is possible. So that's a problem. So uniqueness of the solution is not possible, which is similar to the problem we have handled in fluid dynamics, Navier-Stokes equations. So now we move towards numerical approximation to model equations. So first of all, we have to know the necessity of numerical solutions, because the analytical solution is not possible in most of the cases. And in this case, the drift diffusion model or Van Roosbrook equations, it is not possible to go for analytical solution or closed form solutions. So because of the great importance of semiconductor devices in the modern electronic industry, it is always acceptable, or it is desirable, the design and behavior of the device be predicted to know the accuracy in advance of its actual fabrication. So why people are going for simulations? Because actual fabrications takes too much of money, too much of time, so that it is very costlier. So that's why people are going for to study the behavior of this device and the design of the device through this simulations rather than this actual fabrications. So the cost of rectifying the design error at a later stage may be very costlier, and it's not possible. One of the main ways of guarding against such a disaster is to simulate the device using a suitable numerical models. This has given rise to creation of expensive numerical software, both within a larger multinational electronic company and in a small specialized service companies. So for example, we can take up a Samsung. Samsung is doing a lot of R&D works and R&D having a going for fabrication. Before going into the fabrication for small semiconductor device, that is the example of nanoscale semiconductor devices, they'll go for the mathematical model or some other models, simulations. Then they will predict the efficiency, and they will predict the kind of behavior of the semiconductor devices. So here I'm talking about necessity of numerical solutions. So the mathematical analysis of Van Roosbrook equations, largely what is the lacking we are lacking here is that there is also no general theory for this convergence, error estimates, other things, which is used to simulate this semiconductor devices. So the numerical analysis of such methods has usually been carried out only for some linearized form of the problem. So we convert the problem into the simpler one as a sample problem, maybe a very simple one, And we are going to apply this finite element method. And the system of equations is often assumed to be decoupled so that the equations can be studied at one at a time. So once we have to do this decoupling, then it is possible. Therefore, there are no error estimates applicable to the simulations used for practical applications. This gives rise to the need for other criteria to judge whether or not the results of particular simulation are of scientific values. So there are some mathematical properties we will see in this slides. So the drift diffusion model, that is frequently used to model the behavior of the semiconductor devices. And it is expected that solutions of the system of equations which describe the behavior adequately, provided that the model for the physical parameters are sufficiently accurate. Sometimes it is possible to analyze solutions of the coupled system of equations mathematically. And we have to extract these properties of these solutions without knowing anything about the semiconductor devices. Most of the mathematical methods, we are just applying trial and error only. So we cannot predict that this method works very well, this method is not working very well. We are not confined to that most of the time. So we have we believe that some methods will capture this behavior of this semiconductor devices efficiently. We believe it, and we have done it, and we have done some error estimate as well. But sometimes it goes very well, sometimes it will not goes well. So that only we pointed out that what are the issues we are facing. Then so far that time we don't really understand that. That's a point here. And hope that that these properties reflect accurately the typical behavior of the semiconductor devices. So one is a linearized form of the system. So the nonlinear system, nonlinear Poisson equation, we have to go for a simple linearized equations. So for the nonlinear Poisson equations, the existence of solutions directly from this ellipticity of this PDE. And for the complete system of drift diffusion models, equations, the existence of solution cannot be concluded directly. That's a problem here. So, however, the change of variables can be used to transform the continuity equations into self-adjoint equation. That's one another possibility is there. And we call it slab boom variables, which are used suitably linearized the system. That's one form. And I'm not talking about the slab boom variables and all. You just go through, you Google it, and you'll get some of the information about slab boom variables. There's a transformation we are using here. So I'll give some kind of schematic algorithm here. The following steps can be identified in the typical numerical algorithms for obtaining the approximate solutions of a nonlinear system of PDEs. First one is a discretization of the domain. We call it meshing. That's the first part. The second part is the discretization of the differential equations. That's usually we are doing it in a finite difference method. There's some numerical techniques we have done it. And the solution of the resulting nonlinear algebraic systems. That's the third part. And fourth one is solutions of sequence of linear systems. So these are the idea about, this is a schematic algorithm of finding the approximate solutions of nonlinear system of PDEs. And there are some remarks on the algorithm. So the difference between the continuous solutions and we call it exact solutions, and approximate solution is mainly determined by the methods used in the first two steps. So the methods used in third and fourth steps influence mainly the computational time. And although the choice of the method within each of these steps is not necessarily related to the choice of the methods in the other steps. So we can go for the third and the fourth choices of the methods, whatever you want to do, which not necessarily related to the previous one. That is the point. So there is usually some degrees of interdependence there. For example, a rectangular grid is chosen in the first step, and matrices in the resulting linear system have a banded structure, and dedicated methods for such systems can be chosen in the fourth steps. So in that way, we can do it. So furthermore, the choice of the discretization method also influences the properties of the resulting system matrices, which turns into that decisive for maybe it is for choice of the linear solution techniques. The first main step above consists of selecting finite number set of points which solution will be determined approximately. Most discretization methods in the second main step requires a set of points which is based upon subdivision of the solution domain into smaller elements. And this can be done in several ways. For example, if the solution domain has a rectangular structure, then it is conveniently subdivided into smaller rectangular elements. And alternative discretization of the solution domain is obtained when the rectangular elements are subdivided into triangular elements. So it need not be go for smaller rectangular elements. Instead of that, we can go for triangular elements, which is analogous to subdivisions into tetrahedral elements for three-dimensional brick elements. So you know what is the tetrahedral elements in three-dimensional space. I think I hope you understand. All the sides are triangles. And if the solution domain is not of a rectangular structure, it is often more convenient to cover it with a triangular or tetrahedral element. So this task should be carried out preferably automatically by the mesh generation program. I will tell you what is the mesh generation program and all. So there is a kind of, in MATLAB, people are doing it as a function files, function M files. So they will generate the mesh automatically. Whenever we need, we just carry taken up code taken up from this function M files. So once a mesh has been generated, the solution can be determined approximately at special points, which is associated with this mesh. And these are the numerical approximation strategies. So we have to obtain, in order to obtain this equations for the approximate solution approximate solution values at selected points. So the differential equations and the boundary conditions are then discretized. Already I told you that we have to the discretization of the differential equation is very important. And after that, along with that, we are doing it discretization of boundary conditions as well. So a variety of techniques is available for this task. I think some of these techniques require only the coordinates of the selected points, whereas the other techniques make use of the subdivisions into elements of the solution domain. So a well-known example of the first one is the finite difference method. That is what I am doing, discretizing the differential equations and also discretizing the boundary conditions as well. But in which the derivatives are in this finite difference method, the derivatives are approximated by divided differences. We'll call it d plus d minus or d plus minus and all. So an approximate solution on the entire domain can be obtained by the piecewise polynomial interpolation of values at the selected points. So an example of such one is the finite element method. So what I am doing this here, I am applying the finite element, choosing this finite element method to solve the system, solve these equations. So which makes use of the underlying structure of the mesh. And in fact, the finite element method generates approximate solution values on the entire solution domain, but I am by assuming that the function is a polynomial on each of the element. So there is some kind of disadvantage of this method is that we cannot do it on a single point. We can go for the entire domain of this my interest. So that is the biggest disadvantage which I feel. That's also true. So for semiconductor device simulation, the finite element and finite value method is most popular discretization techniques. And we have to consider this differential equations, which is a conservative form that grad dot f of u is equal to g of u. So this u is a known function and g and f are known. And you know that what is grad and all, the definition of grad. And f of u is a flux. And integrating this equation over an arbitrary subdomain capital B, whose boundary is dou B, and by using this Green's formula for the integral of this left-hand side integral over dou B, f of u dot n cap is a unit normal vector, is equal to integral over B g of u. So this integral on the left-hand side is then approximated by the finite sum of the form. Almost it's nothing but your integral as summation. So f of u dot ni is a normal component at some point on an associated small part of the boundary. And this Li is a length. That boundary, the small part's length, that is what Li. This integral on the right-hand side can also be approximated in a similar way. So using only the finite number of values of g of u only, that's enough. So so far we have come across Boseman transport equations and Van Roosbroek equation. That is one Poisson equation, and another one is a kind of system of two equations, first order equations, and so all this system nonlinear PDEs are solved by most of the methods, that is a numerical methods, or either numerical method or some approximation methods, we call it semi-analytic methods and all. So far we have done it, and all these problems can be solved by finally being solved by finite element method. So the advantage of finite element method is very enormous, and it deals with the complex geometry, complex material property. As I told you that the semiconductor device having a different materials, on one domain it has one material, the next domain it is another material we are using. So we are having a different material properties on the single device. So we want to study the single device with a different material property, the complex geometries. Definitely this finite element method will works very well. So this is a sample problem which I am showing in this slide. I'm going to apply how the finite element method effectively applying this problem. This is a second order problem, ordinary differential equations with the homogeneous boundary conditions, that is u of 0 is equal to 0, u of 1 is equal to 0, and my domain is omega. Omega is a domain, is an open interval 0, 1, and satisfying some of these properties. And b of x, u of x, f of x are known functions or coefficients. U is unknown functions. And these known functions are sufficiently smooth. That's what we call sufficiently smooth, as many as times I differentiable functions. And I'm constructing the test space. I'll tell you that capital V is a test space. I'm taking up this small v that belongs to space, capital V, and multiply this small v in this equation number 29, and left-hand side as well as right-hand side, and taking integration over 0 to 1. And the first term is minus integral over omega u double dash into v into dx. So I'm applying using this integration by parts techniques. So once I am applying the integration by parts technique, the first term vanishes. You can apply that v of 0 is equal to 0 and v of 1 is equal to 0. So the first term vanishes. Second term is integration over 0 to 1, u dash of x, v dash of x. And the rest of the things, simply I am putting here integral over 0 to 1, b of x u dash, beta into dx, and plus integration over 0 to 1, uc times of uv into dx. So right hand side is also same as that. So this integration over 0 to 1, u dash, v dash can be written as a, we call it inner product. It is something very interesting. We call it as an inner product. That is what we call it, L2 space and all. Forget about these things, right? Don't worry about all this, this L2 and all, H01 and all. Just simply I'm saying that it's an inner product, right? Plus this also is inner product. This also a third term is also inner product, because integral of f into v is into dx can be written as inner product of f comma v. That's all. That much is enough to understand all these ideas. And this, I told you, this capital V is a test space, right? The test space is nothing but H01 of omega. That is what we call the Sobolev space. I think special Sobolev space that's satisfies set of all V such that this V and V dash belong to L2 space, square integrable space. That is L2. We call it L2. And V of 0 is also 0 and V of 1 is also 0. So in such a way that the first term vanishes. We are choosing that V of 0 is equal to 0 and V of 1 is equal to 0. That's why the first term vanishes here. And in this slide, we will have some weak or variational formulation. So the previous problem is considered, and for that problem, this is a weak formulation or variational formulation. We call it B of u comma v is equal to f star of v. That B of u comma v is u dash v dash plus inner product of v u dash comma v plus inner product of c u comma v is equal to f star of v. F star of v is nothing but inner product of f comma v. So that I can write down this equation number 32, we call it a weak formulation or variational formulations. So a problem which I am showing here in this slide, well, I think this is equation number 29 to 31. So this is a differential equation, boundary value problem with the homogeneous regional boundary conditions. This is a problem, I call it a strong problem. This strong problem is turned into kind of a weak problem. So that is a strong solution. The solution of this equation number 29 to 31 is called a strong solution because the problem is a strong problem. And now I convert into or transform into a weak problem 32, which is called a weak problem and whose solution is nothing but a weak solution. And I define something like norm and all. We call it energy norm, associated energy norm and all, through this L1 norm and L2 norm. This is the L1 norm, this is the L2 norm, right? And I define it. And this is the existence and uniqueness of weak solution. Is established by using Lax-Milgram lemma. It's a very fantastic, very interesting lemma, which gives us existence of and uniqueness of the solution. This weak solution, of course, it should satisfy the conditions. B is a bilinear form which satisfies this condition, which is continuous. That is a property I am write down here, statement. And another one is B of this one is a Corsi property or B elliptic property satisfying this one. So if both those conditions are satisfied, then I am saying that's this Lax-Milgram lemma we can apply, and which gives us a existence and uniqueness of a weak solution. So this is a lemma. I think I just show you that something like yeah. So we go for the discrete problem. I told you that first one is a discretization of my domain. Second step is discretization of my differential equations. So I have done it both the things here. Discretization of the domain is 0 to 1 is discretized, as well as the problem, weak problem is also discretized. So this is called a discrete problem, equation number 33. And I am looking for the solution in capital V, so that I am taken up an approximation space. VH is my approximation space, the solution that belongs to VH. that UH belongs to VH. And this VH is spanned by the finite number of linearly independent elements, that is P1, P2, and so on, Pn minus 1. That is a basis for me, this for VH. This phi is nothing but looks like this function, and this looks like a hat function. You can see that hat functions, this is a phi of x, phi of x is exactly hat functions. And discrete energy norm I defined, which is associated with the discrete space. I am defining a discrete energy norm, and which satisfies the properties of conditions of Lax-Milgram lemma, so that from that I can find the unique solution as UH is summation over I is equal to 1 to n minus 1 UI into phi of x. So my discrete problem is this one. This is a discrete problem. If we have a difference scheme, the equation number 34, we can solve it. Yeah. So so far I am explaining the finite element method. Now this method, finite element method, is I'm going to apply this method into my Van Roosbrook equations. That Van Roosbrook equation is modified again as one is a Poisson equation, another one is a kind of second equation, which is this is a Poisson equation. It's a something a parametric form. So parameterized this in polar coordinates, this r comma x, and this is a parametric form of this Poisson equation. And I'm going to solve this is by using this finite element method to this problem. And this is a two-dimensional problem. And if your semiconductor device is smaller and smaller, how far the semiconductor device is smaller is something like 10 nanometers. The whole device is like a 10 nanometers. You cannot see as in empty eyes. In the microscope only you can see that semiconductor device. This is a nanoscale semiconductor devices. So for that devices, we are considering also a Schrodinger equation. This is a Schrodinger equation I am considering. And here that psi naught is a wave function. That psi naught is a wave, and H delta is a very small quantity. This mx is a mass, is electrostatic potential here, E naught. And this capital UK is your surface potential taken up from approximating from the solution of this Poisson equation. That is my UK of r comma x. Okay, and for this is a problem I am considering for MOSFET. I already told you, metal oxide semiconductor device, field effect transistor, MOSFET. We are considering this kind of model. This is a coupled equation. One is a Poisson equation, another one is a Schrodinger equations. From that, what I am doing here is I am approximating the surface potential, maybe the known parabolic curve, to approximating that surface potential. From that surface potential, I am using it in the second equation. The second equation is Schrodinger equation. So this Schrodinger equation is a singular perturbation nature. So that is H delta the whole squared by 2 mx star. This is a small parameter. That is my epsilon. So epsilon, we have done it, right? We have seen this equation. See, this is the equation I'm considering in the slide number. For this equation, I'm not showing it. Okay, anyway, the Poisson equation epsilon is there, right? Okay, anyway, I will see later on. I think I'm not showing here that epsilon. So epsilon is a small parameter. That epsilon is that parameter is influencing this differential equation largely. And for that small parameter, I am applying the singular perturbation theory to this kind of problems and getting the approximate or numerical solution of this system. This is a architecture of the double-gated monolayer MOS2 transistor. This is source and this is drain. So this is MOS2 and this is a gate, double gate. This is the oxide layer, substrate. So this is symmetrically structured double-gated MOS2 transistors. And the channel and the source drain regions are doped with the N and the P-type impurities as well. So this is a mathematical model of double-gate MOSFET, and whose solution is that is a potential function phi of phi is derived this one. Analytically, we derived it. This is the architecture of the multi-gated transistor. So we are going for a three-dimensional system of equations. One is a Poisson, another one is a Schrodinger equation. So this is a multi-gated MOS2 transistor. And this is a simple one-dimensional Schrodinger equations. So we are all having a mathematics differential equations that is which models semiconductor devices in nanoscale structures. So these are my references, and I'm not showing any MATLAB program here. Actually, I'm not doing it, and I'm not showing here. Thank you very much. Now the questionnaire session.
Yeah, Shruti, we have any questions?
Not yet, sir. We didn't receive any questions yet. 1 second, sir. No, sir. We have no questions yet.
Okay. I think there are some in chat box. We don't have any questions.
No, sir. In the chat box, we are not having questions now currently.
Oh,
Yeah.
okay. I couldn't see who are all joining here. I think that's not showing to me, right?
Sir, students joining the the Amrita platform. So through
Okay.
it will be live.
Okay. Thank you very much. Okay. So if no questions, then I can end up my talk.
Okay. Thank you, sir. We can just wait. Students can post their questions in the chat box if you have any.
Yeah.
So we can just wait for a couple of minutes. We can just check.
Sure. I'm waiting. No issues. I'm waiting here.
Sir, I think we can just wind up the session. There are no questions there.
Okay, okay. Thank you. Thank you all.
Okay, sir.
Thank you very
Thank
much.
you, sir, for this wonderful session from your side. And thank you all the students. Yeah. Thank you, sir.
Shall I get this recording is done? I think so.
Yes, sir. Yes, we have recorded. We'll send you, sir.
Okay, okay. If
Okay.
possible, you can just send to me and then
Sure,
I'll
sir.
also
Sure.
view that.
Yes. Yeah.
Thank you. Thank you very much. Thank you. Thank you, sir. Dishant, sir.
Thank you, sir.
Hello. Thank you, sir. Thank you very much.